Good morning. I am very happy to see all of you here. Some of you already participated in the first workshop, Quantum Non-Stationary Systems. It was quite recently, only 14 years ago. Now we decided to repeat it. And um, uh, recently I participated in some conference, and the organizer gave the first talk, and he explained that, okay, I shall give the first talk, after that I shall be free for any other activities. And it was a very good idea from my point of view. Therefore, I decided that I shall open the scientific part, and at the end of this day, I shall speak again, but mainly about not completely scientific, something about funny stories in my life and something about uh, science. Okay, and at the last day of our event, Alexander will finish the scientific part. Okay, now I want to tell you about some results obtained by me and by Alexander recently, last 1 or 2 years. It related to adiabatic invariance of charged particle in magnetic field. And I shall explain you why it seems interesting. The system which we studied is quantum particle in magnetic field. You see the Hamiltonian, and we use the gauge named circular gauge, because in this case all calculations are relatively simple. Other gauges I will show you later give much more complicated formulas. And we can ask why this system is interesting, because it was studied from the very beginning of quantum mechanics. I will give you some references later. And for instance, in the general case, this was done in the well-known papers by Lewis and Riesenfeld and Malkin, Manko, and Trifonov. You see, this is end of 60s, beginning of 70s. What is important, most important part of these papers? That all quantum solutions are determined completely by solutions of simple classical equation of motion, oscillator with time-dependent frequency. And this was done after that papers, dozens of papers by other authors, where people studied different consequences. But the problem was until last years, nobody, at least how I know, nobody considered some concrete time dependencies. All formulas were very nice, but only in general form. And recently, with my former PhD students, Mateusz Orowicz, we decided to see some explicit special cases when everything can be solved exactly. One of these cases was this kind of frequency, initial one, and then exponentially decaying or growing to another final frequency. And what we discovered, we consider the following situation. We have some initial state or ground state or some equilibrium thermal state, and we considered this time evolution, and everything depends on this parameter kappa, which gives us the rate of evolution. Okay, and what happens? You see this ratio of final energy to the initial one, and these numbers correspond to the rapidity of the evolution. If everything is very, very fast, you see these figures, they're totally symmetric. Okay, but if we have very long evolution, you see what we have here. We study begin from some positive frequency, and when we finish, this is a final one. If final one is has the same sign, okay, we have this evolution, straight line. This is adiabatic evolution. And here also straight line. But when we pass through zero, we have also adiabatic evolution, this almost straight line. But you see, inclinations are different. And it appeared some magic number 3. Inclination of this part is 3 times bigger than inclination of this. In the case of initial ground state, if we have initial thermal state, inclination is even much bigger. Okay, this is for this time dependence. And we considered another case, the four well-known Einstein-Eckert profile. And here the straight lines are even more visible. You see what happens. Therefore, we decided to study in more detail and trying to understand these numbers 3, for instance, that energy triplicates after the magnetic field slowly changes its sign. Why this happens? And let us remember what is adiabatic invariance. So everybody knows about adiabatic invariance of the harmonic oscillator with time-dependent frequency. And we know that if frequency changes very, very slowly under this condition, then we have a ratio of instantaneous energy to the instantaneous frequency is constant. Okay? Then we can ask, we change frequency slowly for this one, come to another, then go back. What will be the final energy? According to this formula, okay, it will be the same. But what will happen if we pass through zero, okay, and arrive, for instance, in the case of magnetic field, to the same absolute value, but another sign? For harmonic oscillator, we pass, attain zero, and then come back to the initial value. What will happen in this case? And we have to analyze the validity of this adiabatic approximation. I will show you later in more explicit form that it appears that if we take the solution to the equation, like this modified plane wave, the usual plane wave E omega t, this will be some integral of this. But if we put this solution in the equation, we shall obtain this result. And we want to disregard this term. There are these conditions. You see that derivatives must be small, but we have denominators, omega. So if frequency becomes very, very small, adiabatic conditions are broken. And there were a lot of studies of adiabatic regime during all the history of quantum mechanics. People studied a lot, but mainly studied the case when adiabatic conditions were fulfilled and the people calculated some corrections and so on. But now let us ask, what happens if the frequency passes through zero? And there can be two answers. One, forget about this question, is incorrect because conditions are not satisfied, therefore there is no problem. But I like one classical book of Russian scientists, brothers Strugatsky, book named Monday Begins on Saturday. And one of personages of this book is Cristobal Josevich Junta, and he liked to tell that the real question is what to do with the problem which has been proven to have no solution. And we decided to follow this question and try to understand what will happen. And this references to our recent papers with Alexander. Okay, what we decided to do first. Let us look at the classical problem, the classical harmonic oscillator with time-dependent frequency, time depends in this function f. Parameter tau gives us the rapidity of variation. If tau is small, it is very fast transition. If tau is big, then we have slow adiabatic transition. And what we want to calculate, we want to obtain solutions to this equation for the initial conditions which have the same initial energy, but then initial position, initial velocity will different appear some phase phi. Okay, and consider classical trajectories. Then we will calculate some dimensionless quantities. I define them here. And we want to calculate this ratio, instantaneous energy to the initial one. In these dimensional variances, we have some formula, okay, and appears some important parameter, capital G. This is initial frequency by the duration of the process. So if this G is small, this is instantaneous jump of frequency. If duration is very, very big, then we have adiabatic evaluation. Therefore, what means adiabatic invariant? That means that this ratio for big values of parameter G must not depend on G. It will depend only on this dimensionless time. And it must not depend on the initial phase. For any initial state with the same energy, ratio will be the same, some function of this. And now, what happened? We decided to consider first this uh, simple dependence, some power. And we decided to normalize time the following, that frequency equals zero at time equals zero, okay? So when we have the parameter negative, this means that we have before attain frequency zero, and positive, then we have after. And let us look at this parameter f. If parameter g is not very big, okay, this means that it's not a adiabatic regime. Then we have a strong dependence on phase. You see this phase and this ratio, strong dependence. Agora, now, if parameter g is very big, we used 1000, look at the first glance, the pictures are the same. But pay attention to the scales. Here, scale from 0 to 1, okay? And here, 0.248, and here 0.252. There is actually this practically constant. Practically, there is no dependence on phase. If we increase this parameter, figures will be similar to this, but the region will be diminished. This means that this is really a adiabatic invariance. And now let us look what happens if this parameter t is positive. This means that we passed through zero value. And we see figures very similar, but now we see the parameter g 1000, but we have strong oscillation, strong dependence on phase. And this is for this time dependence, and this is another. What is this time dependence? Constant frequency, then some variations, then constant. This is smooth dependence, smoothly vary frequencies. But figures are very similar. And what is interesting, if we look at these pictures, n equal 2, this means that frequency passes zero in the linear way, And you see this time phase dependence, but there is average value is 3. If we have a parabolic dependence of frequency, we have average value 7. And appear this magic number, 3, 7, and others. And we wanted to understand how they appear. So, I show you that if we calculate average values, you see quite different time dependencies, but graphics are identical. Okay, what is common is that dependencies are different, but the passage through zero is the same, or linear or parabolic, and we have the same figures. And now let us go to the quantum case, because we see that nice lines appeared after averaging over phases. And we know the science where averaging is made automatically. That's quantum mechanics. Every time we calculate average values. Okay? And we go to the quantum case for oscillator. Well, we know that this problem was studied by many people. And classical papers, first paper is by Husimin in 1953. And then people from Russia, Popov Perelomov, Malkin Banko Trifonov, Louis Lisenfeld. Okay. So this case was more or less studied in the general form. Okay. And let us return to quantum problem. I told you already that all quantum results are described in terms of these classical solutions. And we can calculate mean values of coordinate, momenta, mean energy. You see, they depend on mean values, different mean values, and some functions of this function epsilon. It is complex, but it is convenient to use the solution where Wronskian is fixed by this value. And formulas a little bit complicated, but now let us look what happens in the adiabatic approximation when we choose solution in this form. And then if we look at the preceding formulas, you see that there are mean value of x squared, mean value of p squared. But if we put that nice solution here, all these parameters disappear. And what we'll see that the ratio of instantaneous energy to the instantaneous frequency is constant for arbitrary initial values. This is adiabatic invariance, okay? And now we suppose that frequency passes through zero at some time. What happens formally at time much bigger than this instant when frequency goes to zero? Again, adiabatic conditions are satisfied, but we cannot write solution that's exponential with positive phase. There are superposition in quantum mechanics, superposition of positive function and negative, and with constant coefficients, u plus and u minus, okay? And the consequence of this Wronskian is this famous identity of the SU11 algebra. And what will happen in this case? If we calculate now the energy, we obtain generalized adiabatic formula. Then ratio of instantaneous energy, mean energy, to the initial value, okay, proportional to the frequency. And what coefficient of proportionality? It does not depend on time, okay? And there are two parts. One is determined only by these coefficients u plus and u minus. Another part, it depends also on some initial values, initial state. So in order to simplify calculations, we consider special case of initial states satisfying this condition. This includes vacuum, thermal, Fock initial states. Then we have very simple formula. You see, only this. From this formula, we can see immediately that energy always increases when frequency returns to initial value. Okay, and what else? Now we can consider some special cases of frequency, the same that we used in the classical evaluations. This potential, and it is well known actually. In this case, the equation for oscillator can be reduced by some changes of variables to the Bessel equation. And about Bessel equation, we know practically everything. And there are two main parameters. This parameter J, which is G capital, which must be big in the adiabatic regime, and another parameter G multiplied by this parameter nu. Nu is related to this power of our dependence on frequency. Okay, and after that, knowing these solutions, we can calculate everything. We use initial conditions, then we pass through zero, we have conditions of continuity of functions, derivatives, so on. So everything can be calculated, all coefficients are calculated in terms of Bessel functions of different orders. Everything can be done, and we can calculate this ratio in instantaneous energy to the initial one. And there are some formulas, exact formulas. We contain a lot of many Bessel functions, but we know everything about Bessel functions. And now let us look at the result. Now everything depends on some parameter b, okay? And you see how this dimensionless time, how all depends on this power of frequency dependence. And parameter small g, which corresponds small g, this instantaneous change of frequency, all is symmetrical. And big G, you see this adiabatic evaluation. And then when we pass through zero, okay, we arrive with, you see, at this level 3. Exactly. Now, what is the formula? In the adiabatic limit, we have the following thing. In the no, in the adiabatic limit, we see this ratio of time-dependent energy for negative time before we reached zero and positive time after we reach zero. And you see, using formulas for asymptotics or Bessel functions after some work, we arrive at very simple, very nice formulas. You see, 1 minus plus cosinus squared. If we have a negative value before we reach zero, 1 minus cosinus squared, here sine squared, it is, this coefficient is 1. And if we pass through zero, then we have sine plus, and this coefficient beta is given by this formula. Okay? And we calculate exactly that for n equal 2 is 3, for n equal 4 is 7, and many other values. So we understand now how arose that magic numbers. And now we see, okay, this is some repetition of that formulas. Okay, I go further. And for instance, we can analyze what means the adiabaticity. All depends on this parameter G. Adiabatic regime is with G is very small. You see, when we have constant values. Since that what means G must be big? What means big? If the order 100, it is already that we have adiabatic regime. Okay. And now we considered also Epstein-Eckert profile here. Then solutions are more complicated. They are given by Gauss hypergeometric function. But again, we can calculate everything analytically using these solutions. I shall omit some intermediate calculation because we know everything about hypergeometric function. And finally, we obtain, in this case, the same ratio, final energy, when we return to the same frequency, but in the middle, we pass through zero. This ratio will be exactly 3, consequence of exact solutions. Oh, very nice result. And there is some details of the evolution. Actually, you see how evolution happens. Here, when frequency 0, but ratio attains some small minimal value, a little bit earlier we reached 0. Then energy became grow. Okay. And now let us think about the following. What happens if we pass through zero not one time, but several times? What happens in this case? Then if we see that what we obtain, that if we have initial function with positive exponent, then after we pass through zero, there will be combination of positive frequency function, negative frequency function. And now we have passed this solution passed another way through zero. What will happen in this case? We understand that if a function epsilon transforms by this form, complex conjugated function. We'll transfer it as epsilon complex conjugated. And then we can obtain some recursion relations that how final coefficients can be calculated. Some recursion relations, and this identity is satisfied exactly. Okay, and what, for instance, in the case we have two times when frequency goes to zero. This is our coefficient of proportionality. And you see that in this case, it depends strongly on the phase. What is phase? Phi, or phi capital. This is integral accumulated between 2 points, when one point when frequency was zero, another point when frequency was zero. It depends very strongly on this. If we change slightly interval between 2 points when it is zero, coefficient beta will quite different. For instance, this is minimal value and maximum. You see that in principle, minimal value beta can be 1. So when we pass once through zero, energy triplicates. But when we pass 2 times through zero, energy can be the same, but it can be much bigger. In that example, instead of 3, it will be factor 17. Okay, therefore we see that multiple passes through zero give some unexpected evolution. And there are classical illustrations. We consider the function sine squared for frequency. For this function, we have no analytical solutions, but numerically everything can be done. Okay, and you see small variations of accumulated phase 2 pi corresponds to variations of parameter capital G, only 5. And G is of order of 1,000, 2,000, but small variation will change too drastically. Let us look what happens. We have this parameter ratio, okay, dependence on phase. Okay. When we pass only once through zero, you see there is strong dependence on phase, but mean values are the same. Mean values are the same. Now, what happens if we passed once through zero or 2 times through zero? Parameter t capital is 3. And you see strong dependence on this parameter g. When g changes by 5, we have practically the same. But when g changes less than 5, okay, 1 or 3 or 2, you see we can all dependence when we have the same initial frequency, all this extremely big growth. Therefore, we see that if we pass through zero several times, the final evolution is practically unpredictable. Everything depends on the phase accumulated between 2 passes through zero. So from my point of view, it is an interesting result. And we calculated also fluctuations of energy. They're rather high. Okay, it depends on the initial Fock state and so on. And now, very interesting results related to evolution of the Fock states. Okay. It was calculated that if we have time dependence frequency, usual Hermite polynomials maintain their form, but instead of some constant argument, will appear this absolute value of that function epsilon. And we can calculate the expansion of this time-dependent state over instantaneous Fock states. This was calculated also in papers by Popov, Perelomov, Malkin, Manko many years ago, appear associated Legendre polynomials, but nobody made pictures of this dependence. Alexander did this. And well, we can formulate it as generalized Born-Fock theory. We know that the Born-Fock theorem of 28 tells us that if we have slow variation of parameters of Hamiltonian, then quantum numbers are adiabatic invariants, and functions preserve their form with instantaneous value of frequency. Okay, but now we have, when we pass through zero, probability to be in the same state is given by this formula. And you see, if coefficient u plus is 1, this is usual adiabatic regime. We know quite well that Legendre polynomial of argument 1 is 1. This probability is 1. Therefore, this is a usual adiabatic theorem. But what will happen if we pass through 0? Then coefficient u plus not will be 1, it will be bigger than 1. And in the case of linear pass through 0, it will be square root of 2. And now we have exact formulas. And now let us look at the results. What is the expansion of the initial, for instance, 7th Fock state over instantaneous Fock states? You see that energy, we know that energy will increase 3 times. Therefore, we can expect that 7th Fock state will transform into Fock state with number 21. But we know that fluctuations of energy are very high. Therefore, it cannot appear. You see, 7 and here 21. Probability to go to this state is very, very small. And what appears? This probabilities to go to state with 3n, very, very small. And every time probabilities to find the system, the states with quantum numbers less than 3n is about 50%, and 50% it is bigger. And when initial Fock state number grows, you see appears initially some irregular picture, but then picture becomes quite regular. But I did not succeed to find some analytic expression for this regular structure. And this is our adiabatic generalizations of adiabatic invariance in the case of harmonic oscillator. Now we return to the magnetic field. Then everything is very similar, okay? Only some differences, I will show you some differences. What will be the solution? Solution is given by Laguerre polynomials. It is for the first time it was obtained by Fock in 28, and the time-dependent case exactly Malkin, Manько, Trifonov in 70. Okay, and we can expand this solution. Depends now on 2 quantum numbers: radial quantum number and azimuthal quantum number m. And what will happen? We use the same scheme, calculate everything, and what will be generalization of Born-Fock theorem? Here, some probabilities in terms of Jacobi polynomials, and these nice pictures. So we have initial quantum states, for instance, state with radial quantum number 0 and azimuthal quantum number 20. And you see what is interesting. The same azimuthal quantum number, but different radial quantum numbers. N equal 0, we have one peak, but you see peak is rather wide. When we have n equal 5, we have 1, 2, 3, 4, 5, 6. 5 plus 1 peaks, okay? And for instance, n25 we can calculate will be 26 peaks. This appears this interesting picture. This is generalized adiabatic invariance, that when frequency passes through 0, we have time-independent distribution of the quantum state over Fock states, over energy eigenstates. Okay. And nice, we can calculate mean energy. And interesting thing is what happens with magnetic moment. You see classical expression for magnetic moment, okay? So in remembering the formula for the probability currents in the quantum mechanics, we can see that this mean value of this operator. And here, kinetic angular momentum enters again. You see, pi is p minus vector potential, kinetic momentum. Exactly, it enters the game. And we can calculate all average values, so on. And what happens in the adiabatic regime? when we have this condition is satisfied, then mean value of magnetic moment is exactly mean value of energy divided by frequency. This is well known adiabatic invariant in the magnetic field. But when frequency passed through zero, formula is more complicated. You see, will Bohr magneton, and there are some terms which contain time-dependent function. That phi enters the game. But if we make averaging over these fast oscillations in time, for this double averaging, quantum averaging and and time averaging, we have the same formula. This is new adiabatic invariance, double averaging. Okay, so my conclusions. My conclusions is that in the adiabatic regime, energy is proportional to the instantaneous frequency, but proportionality coefficient determined by the exponent of the frequency time dependence near zero. After multiple passages, coefficients are extremely sensitive to the total phase. Okay? And the magnetic moment becomes adiabatic after additional averaging over time-dependent oscillations. And this is generalized Bock-4 theorem. But before finish, I would like to attract your attention to the unsolved problems. Unsolved problems is the following. We made everything for the circular gauge of vector potential. But there are other gauges. For instance, Landau gauge, when this circular gauge, what does it mean? This parameter alpha 0. Landau gauge alpha equal 1. What is the difference in the Landau gauge? In the circular gauge, we have to know only function epsilon. In the Landau gauge, we need to know more functions, integrals of epsilon multiplied by the frequency. And what was the problem until now? We can calculate epsilon, but epsilon is complicated functions, or Bessel, or hypergeometric function. And to calculate this indefinite integral, until now I did not succeed to do this. Therefore, the case of Landau gauge is much more complicated. And how this alpha appears? Very simple. Let us think that we have current passes through that rectangular. Okay, okay. How to show this passes there? If we have square, then in this middle of square, we shall have vector potential with alpha equal to 0. It will circular gauge. But if ratio of these sides of rectangular is different from 1, then we shall obtain general situation. For this situation is quite natural. But what happens in this case still now is not known, because this was my first publication in 72 about exactly of behavior in the case of the Landau gauge. Okay, and that time it was shown that formulas will be very complicated. You see, for circular gauge, we need to know only function epsilon. Now we have a lot of different combinations. We have to calculate everything, but how to integrate it analytically, I do not know. So for in the adiabatic approximation, when it is valid, then the ratio does not depend on choice of gauge. Landau gauge, circular gauge, the same. But when adiabatic conditions are satisfied, when they are not satisfied, I don't know, and I suspect that the result will depend on the gauge. Why? Because we calculated with Mateus or Rovitz the situation when we have non-adiabatic evolution. And you see different quantities like ratio of energy. This is circular gauge, this is Landau gauge. Qualitatively, quite different. So what will happen with different alphas is still a problem to solve. And okay, this is the same. And there are these basic papers which I had in mind. Papers with Mateus, there were much more papers with him, and recent papers with Alexander. Okay, that was. I was amused by these results. We explained these magic numbers 3, 7, and others. And it seems to me that this is interesting. And there is a large field of further investigations for young people. So, thank you very much for attention.